This is the output from a half-wave rectifier. In a previous lesson, you learned that the peak amplitude of this output pulse is equal to the peak amplitude of the secondary voltage. But notice that we only have the output pulse half the time. The other half of the time, there's no output at all. Here's the output from a full-wave rectifier. Now we have an output pulse all the time, but notice that its peak amplitude has decreased. This is because the full-wave rectifier uses a center-tapped transformer, making each output pulse only 1/2 as large as the peak voltage available from the transformer secondary. Here's the output from a rectifier that combines the best features of the other two rectifiers to produce an output pulse all the time that is still the same peak amplitude as the peak amplitude of the secondary voltage. It's called the bridge rectifier and is the subject of this lesson. Remember now, the half-wave rectifier produces all the secondary voltage, but it only does it for half the time. The full-wave rectifier produces half the secondary voltage, but it does it all the time. And the bridge rectifier that we're going to study produces all the secondary voltage, and it does it for all the time. 3 different rectifiers, 3 different outputs. And yet, they all operate on the same basic principle, electronic switching of the transformer secondary. We're going to discover this principle by tracing the development of these rectifiers. Because by understanding this simple principle, you'll be able to name each component in the bridge rectifier circuit and know exactly what its function is. You'll be able to trace current flow through the circuit. You'll know how to calculate all the voltages in the circuit, and you'll know how to troubleshoot the circuit. All these things you'll learn in this lesson on the bridge rectifier. Now you might be wondering, why so many different types of rectifiers? Well, like so many other developments in electronics, rectifiers have evolved through several stages. At first, they were simple devices because the need for their output voltages was not extremely critical. However, with the development of more sophisticated equipment, the need for more exact, more powerful output voltages arose. The half-wave rectifier is limited in the amount of current it can supply to the external circuit. Additionally, its average DC voltage output is less than 1/3 of its peak secondary voltage. For these reasons, its use is limited to very low power applications. Even the full-wave rectifier has its limitations. Though able to supply more current to the external circuit than the half-wave, it is still a relatively low power device. And because it requires a center-tap transformer, only half the available secondary voltage is felt in the output. Another limitation of the full-wave rectifier is the peak inverse voltage applied to each non-conducting diode. It is double the output voltage. Now this means that rugged diodes and rather large transformers are needed to supply high output voltages. There is a definite need, then, for a rectifier without these limitations. The bridge rectifier meets this need. I'd like to show you now the really simple principle on which the bridge rectifier operates. Remember, earlier it was stated that the principle was electronically switching the transformer secondary. Now the transformer is connected to a 115-volt AC power source. The load represents the current drain on the circuit. During 1/2 of the input alternation, the voltage across the secondary will appear like this. Positive on the top and negative on the bottom. Now, pay particular attention to this next step. At this time, electronically, the bridge rectifier does this. Connects the load to the top or positive end of the secondary and grounds the bottom end of the secondary. Now, this electronic switching occurs as soon as the top of the secondary goes positive and terminates when it starts going negative. When the input reverses, the top of the secondary becomes negative and the bottom becomes positive. Now, the bridge rectifier electronically switches the transformer connections like this. The load is connected to the bottom or positive end of the secondary, and the ground is connected to the top or negative end of the secondary. Now notice that the load is always connected to the positive end and ground is always connected to the negative end of the secondary. This is true if we want a positive output voltage. Of course, if we want a negative output voltage, all we do is arrange the bridge rectifier circuitry so that the load is always connected to the negative end of the secondary and the ground is always connected to the positive end. With this arrangement, the output voltage is negative. But since the bridge rectifier is mostly used to produce positive output voltages, that is the arrangement which we will concentrate on in this lesson. Now that we have a basic understanding of the principle on which the bridge rectifier operates, switching of the load and the ground connections to the transformer secondary. Now don't lose sight of this simple principle, because by understanding this, you'll have no trouble understanding any aspect of the circuit. To make certain that you do understand this principle, let's have a little test. Now in your TVI guide, under item 1, you'll find 4 diagrams. Now you're asked to draw in the connections to the load and to the ground for each diagram. Oh, and be sure to check the output voltage in each case before drawing in the connections. Okay? Here's the first one. The output voltage in this case is positive. So where is the load and the ground connected? That's right. The load is connected to the positive end of the secondary, and the ground is connected to the negative end. Now this output voltage is negative, so where is the load and the ground connected? To produce a negative output voltage, the load must be connected to the negative end of the secondary, and the ground must be connected to the positive end. Now you do the next two on your own. Now, since everyone passed the test, let's go one step further and determine exactly how the load and ground connections are switched by the bridge rectifier circuitry. Here's a mock-up that will give you a little better understanding of how this occurs. Actually, there are 2 switching actions that occur on each alternation of the input. This switch changes the load connections from the top of the secondary to the bottom of the secondary. And this switch connects the ground to the other end. As you can see, they work together. When the load is switched to the top of the secondary, the ground is switched to the bottom of the secondary. When the load is switched to the bottom, the ground is switched to the top. And it's that simple. Back and forth, as the input changes, always connecting the load to the positive end of the secondary, always grounding the negative end. Now watch as a few output pulses are generated. Notice that the output voltage is positive. This is because the load is always connected to the positive end of the secondary, and the negative end is always grounded. Of course, a mechanical switch like we used is not suited to the rapid changes of the AC voltage, so an electronic switch is used. The solid-state diode is the electronic switch. As you know, the diode will conduct in one direction only. When a positive is applied to the collector and a negative to the emitter, current will flow. The diode is said to be forward biased. With negative on the collector and positive on the emitter, the diode is reverse biased and current will not flow. It's this on-off characteristic of the diode that makes it an ideal electronic switch. So let's now determine exactly how the diode is used in the bridge rectifier to accomplish the electronic switching of the load and the ground connections. First, let's see how the ground is switched. With this polarity on the secondary, we must connect the bottom or the negative end of the secondary to ground. Now this diode is connected so that its collector is always at ground potential. In order for it to allow current to flow, its emitter must be negative with respect to its grounded collector. So anytime this end of the secondary goes negative or below ground potential, the diode becomes forward biased, conducts, and connects this end of the secondary to ground. When the input reverses, this end of the secondary is positive or above ground. The diode is reverse biased, will not conduct, and opens this path to ground. Another diode connected to the top of the secondary will accomplish the same thing. It'll connect the top of the secondary to ground when it's negative and open this path to ground when the top of the secondary is positive. Now watch as these two diodes work together to always connect one of the two switching actions necessary to the operation of the bridge rectifier, switching of the ground connection. Now, let's see how the load connections are switched. Actually, it's done the same way. This diode will conduct any time the top of the secondary is positive and connect the load. This diode conducts when the bottom of the secondary is positive and connects the load. Now watch as all four diodes work together to electronically switch the ground and the load connections to the secondary. With positive on the top and negative on the bottom of the secondary, CR4 conducts to ground the bottom end. At the same time, CR2 conducts to connect the load to the top end. Both CR1 and CR3 are reverse biased and will not conduct. Current flows in this direction up through our Sabell, producing a positive output voltage for the load. When the input reverses, CR1 becomes forward biased, conducts, and grounds the top of the secondary. CR3 conducts to connect the load to the bottom end. Current flows in this direction, still up through our sub L, still producing a positive output voltage. Now notice that in both instances, current flows the same direction through the load. So the output voltage is always positive. Okay, that's how it works. The diodes electronically switch the ground and the load connections to the secondary. Now we can complete item 2 in the TVI guide. The transformer, T1, couples the input to the bridge rectifier. The load resistor, R sub L, develops the output voltage. CR2 and CR3 switch the load connections. And CR1 and CR4 switch the ground connections. Now, let's complete item 3 in the TVI guide. Show the path and direction of current with this polarity on the secondary. All right, from the negative end of the secondary, then up through CR4 to ground, then from ground up through R sub L, and on up through CR2 and on to the positive end of the secondary. When the input reverses, current flows from the negative end of the secondary down through CR1 to ground, then from ground up through R sub L, and then down through CR3 and on to the positive end of the secondary. Okay, what have we learned now about the bridge rectifier? It produces all the secondary voltage all the time. Right? This is accomplished by electronically switching the ground and load connections to the secondary. Correct. And remember, the electronic switching is accomplished by 4 diodes. Yes, CR1 and 4 switch the ground connection, and CR2 and 3 switch the load connection. They all work together to cause current to always flow the same direction through the load. This provides an output that is all positive. Very good. You're a good student. Now let's go a step further and discuss the voltages present in the circuit. Remember, earlier we stated that if you understood the principle on which the bridge rectifier operates, you'd have no trouble calculating any voltage in the circuit. Now, I'd like to show you exactly why. With the load always connected to the positive end of the secondary, and ground always connected to the negative end, couldn't we simplify this and say that the load is always in parallel with the secondary? Look at this. Positive on the top of the secondary, the same positive on the top of the load. Ground on the bottom of the secondary and ground on the bottom of the load. The load is in parallel with the secondary. Now it should be obvious that whatever voltage is felt on the secondary will also be felt on the load. Now knowing this, calculating voltages in the bridge rectifier simply boils down to what is the secondary voltage. Now there are a couple of points to remember when calculating the secondary voltage. First, is there a step-up or step-down ratio between the primary and secondary windings of the transformer? Now here we see a 1-to-1 ratio, which means that the secondary voltage is exactly the same as the primary or input voltage. A 1-to-3 ratio, shown schematically like this, simply means that the secondary voltage is 3 times the primary voltage. Now if no ratio is indicated, then it's assumed to be a 1-to-1. The second point to remember is this. When converting from primary voltage to secondary voltage by multiplying with the step-up ratio, the secondary voltage only changes in amount. Now if the input is given in its effective value, then the secondary voltage will also be in its effective value. If the input is given in its peak value, then the secondary will be determined in its peak value. So the first thing to do in calculating any voltages in the circuit is to use the transformer ratio, if any is indicated, and then determine the secondary voltage. Once you've determined the secondary voltage, it's simply a matter of using the right formula to determine any voltage value in the circuit. For example, here's the formula used to convert effective voltage into peak voltage. E peak equals E effective times 1.414. These and other formulas you'll need to learn are shown under item 4 of your TVI guide. This formula is used to convert peak voltage into average voltage. E average equals E peak times 0.636. Now remember, this is the peak secondary voltage in this case. Here's the formula used to convert effective voltage to average voltage. E average equals E effective times 0.9. Under item 5 in the TVI guide are several problems for you to work out. Now, I'll work the first one along with you, and then you can do the others after the lesson is over. Now, this first problem indicates only the input voltage, 115 volts RMS. Now, that's the effective value. We're asked to determine the peak secondary voltage and the average output voltage. Well, the first thing to do is determine the secondary voltage using this step-up ratio of 1-to-3. So 115 times 3 equals 345 volts. That's the effective secondary voltage. Now we can convert the effective voltage to peak voltage. Substituting, we have 345 volts times 1.414 equals 488 volts. And that's the peak secondary voltage. Now we can convert the peak secondary voltage to average output voltage. Substituting and working the problem out shows that the average output voltage is 310 volts. Now we could have converted the effective secondary to average using this formula, but you see the answer is still the same, 310 volts. Another voltage to be considered is the peak inverse voltage present in the circuit. This, you'll recall, is the voltage that's felt across the non-conducting diode or diodes in the reverse direction, from collector to emitter. Now each diode has a so-called breakdown voltage that, if exceeded, will destroy the diode. For this reason, transistor manuals will list the PIV, the peak inverse voltage rating, for all diodes. Now this rating specifies the maximum reverse voltage which can be applied to the diode before breakdown occurs. In all applications, a diode having a more than adequate PIV rating should be used. For example, in a circuit with a maximum peak inverse voltage of 200 volts, the PIV rating for all diodes used in that circuit should be at least 300 or 400 volts. Now, this safety margin will protect the diodes against voltage surges. To determine the maximum PIV in a bridge rectifier is as simple as determining the peak secondary voltage, because PIV is equal to the peak secondary voltage. Let's assume, for example, 300 volts effective on the secondary and see what inverse voltages are felt on the non-conducting diodes. With this polarity on the secondary, CR2 and CR4 are conducting, and they'll act like short circuits. So let's show them that way. Now let's rearrange the circuit a bit to get a clearer view of how the inverse voltage actually appears to the non-conducting CR1 and CR. Actually, T1, CR1, CR3, and R sub L are all in parallel. So whatever voltage is felt across the secondary of T1 is also felt across CR1 and CR3. Both collectors are at ground. Both emitters are at a positive 300 volts effective. But we're looking for the peak inverse voltage. So we must convert this 300 volts effective to its peak value. Remember the formula? E peak equals E effective times 1.414. So the peak inverse voltage, in this case, is 424 volts. When the input reverses, CR2 and CR4 feel 424 volts peak inverse voltage also. All the diodes feel the same PIV, the peak secondary voltage. Now, the final subject of this lesson is troubleshooting. This is simply a matter of understanding the circuit operation and analyzing the symptoms of malfunction. Now, here is a view of the normal output from the bridge rectifier. Let's put a trouble in the circuit and see if we can determine what's causing it. Notice that all of the output is gone. Our symptom of malfunction then is no output. Now, what could cause this problem? Well, the first thing to check, of course, is the fuse. If it's blown, you will have no output. But let's assume for now that the fuse is good. So what else do we check? Remember, there are two distinct paths for current flow in this circuit. One path is used to produce one pulse in the output. The other path produces the other pulse. But notice that some parts of the circuit are common to both current paths. The transformer, some of the connecting wires, and the load resistor R sub L. So it's logical to assume that if both pulses of the output are affected, as with no output, the trouble must be in some part of the circuit that is common to both current paths. So with no output as a symptom, we check the transformer for possible open primary or secondary winding, the common connecting wires for possible breaks, and the output resistor R sub L for an open. Now let's look at another possible symptom you might encounter. Here we see a normal half-wave output. Normal, that is, for a half-wave rectifier, but definitely not normal for a full-wave bridge rectifier. This indicates that the bridge rectifier is now operating as a half-wave rectifier. And that, of course, is not as it should be. So what's the trouble? Well, obviously, one of the two current paths is open, the one that's required to produce this missing pulse. From the schematic, we can see that this narrows the trouble down to the 4 diodes, one of the 4 diodes, or perhaps one of the common connecting wires to the diodes. Well, the diodes are the most likely source of failure, so we could check each of them for an open. With only half-wave output then, look for an open diode as the most likely source of the trouble, or perhaps one of the connecting wires might be open. Now notice the fuse on the trainer. If a short circuit develops somewhere in the rectifier, the resultant excess current drain will probably blow the fuse. Actually, that's the purpose of the fuse. It's designed to be the weakest link in the circuit, to burn open if excess current suddenly flows through it. Now when it opens, it stops all current flow in the circuit, thus protecting all the more expensive components. Now an open fuse produces a no output symptom, but remember, if you find a blown fuse, look for the short circuit that caused it to burn open before you replace it. Now item 6 in your TVI guide lists several troubleshooting problems. I'd like you to work them out when this lesson is over. Just remember that if the symptom is no output, then the trouble must be in a component that's common to both halves or both pulses of the output voltage. If the symptom is half-wave output, the trouble must be one of the diodes, or perhaps one of the connecting wires to the diodes. And that's the bridge rectifier. It's a couple of electronic switches, a transformer, and a load. CR2 and CR3 electronically switch the load, and CR1 and CR4 electronically switch the ground. These two switches, or pairs of diodes, work together to utilize all the secondary voltage all the time. This, of course, was the bridge rectifier's chief advantage over other rectifiers. Because the load is always switched in parallel with the secondary, the peak secondary voltage, the peak output voltage, and the peak inverse voltage are all the same in the bridge rectifier. When troubleshooting and the symptom is no output, look for trouble in one of the common components. If the symptom is only half-wave output, it's probably caused by an open diode. And there you have it, the solid-state bridge rectifier. Now later on in the course you will study the vacuum tube bridge rectifier. Confidentially, they both work exactly the same.